right, so we're going to talk about difference quotient and rate of change again today. So the warm up here says compute the difference quotient. Now, if you remember from yesterday, our difference quotient is, we call it delta y over delta x. That's a change in y over the change in x. And really all this is a slope formula, but it's just doing it in a different fashion. This is f of x plus h minus f of x. So that's your y2 minus your y1 over, and when you do your x2 minus x1, you end up with h, which is the difference between x1 and x2. So if I was doing this on the interval from x1 over to x2, the h represents the distance in between those two values. So if I'm going to do f of x plus h, all right, delta y over delta x, I need to substitute x plus h in for x. So that's going to be x plus h squared plus 6 times x plus h. So there's my f of x plus h minus f of x. Well, f of x is just x squared plus 6x. X squared plus 6x all over h. All right? So let's do some multiplication here. X plus h times x plus h. All right, if we need to, you can write it off to the side, do it however you want. All right, but I'm going to do it. X times x is x squared. X times h is xh, and I get another xh in the inside terms. So that's plus 2xh. Right there. H times h is h squared. And now I've got 6 times x plus h, which is 6x plus 6h. And then I'm going to subtract f of x, which is minus x squared minus 6x. All of this belongs over h. Now, here's the cool thing about this. When you go to do this, there's some stuff that should cancel out. Your lead terms should always cancel out. Your terms without any h's should always cancel out, just like that. So now what we have left is we have 2xh plus h squared plus 6h all over h. Now you'll notice all of my numerator terms contain an h, so I can actually factor out an h here, and I'm left with 2x plus h plus 6 all over h, and then I can cancel the h on the top and the bottom, and so delta y over delta x is equal to 2x plus 6 plus h. So that formula will compute the slope between any 2 points now on the graph of f of x. And that's what we're going to do in the next part here. It says use the difference quotient to find the average rate of change in the intervals -3 to -1. So let's just start with that one. If I'm going to go from -3 to -1, all right, the first thing I need to know is I need to know what h is, because the -3 is the x in the formula. So this is my x1 here, and this x in the formula right here, this is also considered x1. All right, so h is equal to x2 minus x1, so -1 minus -3, so that gives me an h value of +2. Remember, h is a distance from the first x to the second x, so your h value should be positive, okay? So delta y over delta x is equal to 2 times x1, so that's going to be -3, plus 6, and then +2. So the rate of change here is -6. Plus 6 is 0, plus 2. The rate of change in the interval -3 to -1 is 2. Now, I don't even know what this graph looks like. I don't know where these two coordinates are. I don't know the y values, but I do know that the slope from -3 to -1 is going to be 2 units. Okay? And where this comes in really nice is when we're doing this with decimals like the second one here. So we have the interval 0 to 0.5. So hopefully it's easy to see that h is just 0.5. 0.5. So my x1 now is actually 0. So delta y over delta x is equal to 2 times 0 plus 6 plus 0.5. So the slope from 0 to 0.5 is going to end up being 6.5 units. Got a lot steeper in that area right there. All right. Let me see. Part C says find the points for each of the endpoints. Find the points for the endpoints of each interval. So now what they're asking me to do is actually asking me to find the y values that go with these. So in the interval -3 to -1, they want me to find the y values that go with that. So I want to know what is f of -3. So using f of x from above, that would be -3 squared and plus 6 times -3. So that's going to equal 9 minus 18. That's going to be -9 right there. So I have the point -3, -9. And then I also have the point f of -1. That's going to be -1 squared plus 6 times -1. And that's going to equal 1 minus 6 is -5. All right? So it says find the points for the endpoints of each interval. So there's my first interval there. So I have 2 points here, -3, -9. And I have the point -1, -5. So that's the first one. And we'll see what it says to do in a minute, but I'm going to find the second one here. So my second interval was 0 to 0.5. Well, 0 is going to be an easy one to plug in because f of 0 is 0 squared plus 6 times 0, which is 0. Nice. F of 0.5, not so nice. So let's see what we got here. F of 0.5 is going to equal 0.5 squared plus 6 times 0.5. Now, for some of you guys, it might just be easier to think about the 0.5 as a half, because a half times a half is a fourth. So I can do that, or I could do 0.25. Plus 6 times a half. Half of 6 is 3. So this is really just 3 1/4. All right, or 3.25. I'll go back to decimals here. So I have 2 points here. I have 0, 0, and I have 0.5, comma, 3.25. All right, so that's all they were asking for in that second section there. It says graph the equation and the points from part C and draw the secant lines for each interval. What do the secant lines indicate about the rate of change as x goes to infinity? All right, so my graph, now I need to go back to f of x. So I'm going to go back to f of x here. F of x was given as, let me see, x squared plus 6x. Now, one of the things I can do to graph this is find the x-intercept. So I'm going to do that first. I'll do 0 equals x squared plus 6x. And then I know I can factor out an x here. So I get x plus 6. And so I've got two x-intercepts, one at x equals 0 and one at x equals -6. So I've got 0, -1, 2, 3, 4, 5, 6. So there's -6. All right. Now, one of the other things I can do is, now I know that because my zeros are at -6 and 0, I know my vertex has to be halfway through there. Okay. So because this is a parabola, all I got to do now is I got to find f of -3. So that makes it a little bit easier on me. And actually, if I look up above here, I've already got it. It's -3, -9. We've already done it. So I'm not going to be able to fit -9 going up and down on this scale. So I'm going to do this, the y-axis by 2's. All right. So here we go. -3, -2, 4, 6, 8, -9. All right. So I know that I've got a parabola that looks something like that. Now, there's a couple other things you can do here. Because the parabola is x squared plus 6x, we know that the next point from the vertex should be up 1 and over 1, because we've done toolbox functions, up 1 and over 1. And then we know that the next set of points should be up 1, 2, 3 and over 1. And up 1, 2, 3 and over 1. And guess what? The next set of points would be up 5. And look at your scale. Up 1, up 2, up 3, up 4, up 5, over 1. Look at that. You can easily draw a nice little parabola based on information from the toolbox functions. All right, so there's my parabola. And then it says to plot the points. So I'm going to go ahead and plot the first 2 points here. I got -3, -9, so that's going to be right at the vertex. And -1, -5, that's this guy right here. And it says to draw a secant line. Now remember, a secant line is simply a line that intersects a curve at 2 points. So that's what I'm going to do. I'm going to draw that line through those 2 points right there. And then I'm going to draw the second secant line. So I'm going to go to my other 2 points that I got, 0, 0, and 0.5, 3.25. Now you can see here at 0.5, that's going to be 1, 2, 3, 3.25 is going to be right about here. Because remember, our scale is by 2s. All right, so I'm going to go ahead and draw this secant line. And if you look at those 2 secant lines right there, it's pretty obvious that the slopes, as that parabola goes out to the right, so we would say as x goes to infinity, as x goes to infinity, all right, those slopes of those secant lines are becoming steeper and steeper. So as x goes to infinity, the secant lines have steeper slopes. And hopefully you can kind of see that based on the parabola. As you move up the right side of that parabola, the slope is getting steeper and steeper as you go up the parabola. And so this indicates the secant lines have steeper slopes, indicating that the rate of change is increasing. So as I move up a parabola, the rate of change increases as we do that. All right, I gotta stop and get a drink of water here. All right, let's see what's next here. Okay, so we're going to talk about an application of the rate of change here, the difference quotient. So it says a construction worker drops a heavy wrench from atop a girder. By the way, if you don't know what a girder is, it's a piece of steel. Top of girder of a new skyscraper. Use the function d of t equals 16t squared to complete each of the following. All right, so d of t is going to represent the distance. It says compute the distance the wrench has fallen after 2 seconds or after 7 seconds. So this formula indicates how far the wrench has fallen. So just some easy math here. What is d of 2? All right, so d of 2 is equal to 16 times 2 squared. 2 squared is 4 times 16. So after 2 seconds, the wrench has fallen 64 feet. Okay, 64 feet. And we do want to make sure we're putting units on this because we do have an application here. So we want to make sure that we're keeping the units correct. D of 7, the distance after 7 seconds is equal to 16 times 7 squared, and that's going to equal 784 feet. That must be quite a skyscraper there if it's dropping 784 feet, okay? So just 2 instances of how far the wrench has fallen after 2 seconds and 7 seconds. And the next part of this says, find a formula for the velocity of the wrench. Now, we haven't talked about velocity specifically, but in calculus, velocity is a rate of change. Okay? Velocity is a rate of change. When you drive down the freeway at 40 miles per hour, your velocity is 40 miles per hour. Okay? Your speed is also 40 miles per hour. Okay? So when it says find the formula for velocity, they're looking for the difference quotient here. So in this formula here, we're going to do not delta y over delta x. I don't want to confuse you by writing delta d over delta, what are we looking at, time here, delta t. But you could do it like that. You could say that this is delta d, let's go ahead and do it, over delta t. So it's the, it's the change in distance over the change in time. So instead of f, we're just using d. So this is d of t plus h, okay, because we're talking about time as our variable here, minus d of t divided by h. All right, so let's see what this comes out to be here. So I need to plug in t plus h for t. So this is going to be 16 times t plus h squared minus d of t, that's just minus 16t squared, all over h. That's the distance in our interval from the first t to the second t. All right, so let's keep going here. I'm going to come back here. I don't know if I'm going to run out of space or not. So t plus h squared. Again, if I need to, I'll come over here. I'll write t plus h times t plus h, and then I need to FOIL that guy. So that's going to be, now I got to remember I got this 16 out front too, so I need to put that back. 16. Now t times t is t squared, t times h, and another t times h, that's plus 2th, and then h times h is h squared, minus 16t squared, all over h. I need to distribute my 16, so I have 16t squared plus 32th plus 16h squared minus 16t squared, and this is still all over h. Now, what do we got here? We should be able to do some canceling with terms, 16t squared, negative 16t squared, and I'm going to go ahead, you'll notice both of my terms that are left have an h in them. I'm going to go ahead and factor that h out. That's going to leave me 32t plus 16h divided by h. All right, cancel off your h's here, and we have delta d, the change in distance, over delta t, the change in time, and that's going to equal 32t plus 16h. Okay? Now, the next piece is actually asking us to use that formula, use your distance quotient, or excuse me, your difference quotient, excuse me, use the difference quotient to find the rate of change in the intervals 2 to 2.01 and 7 to 7.01. So let's just do the math and then see what it is that we're talking about here. Okay, so in the first interval here, 2 to 2.01, hopefully you can see that if you subtract 2.01 minus 2, that your h value is going to equal 0.1. Okay, so when I go to compute the change in d, oops, the change in lowercase d, there we go, over the change in t, in that first interval, it's going to be 32 times x1, which is 2, plus 16 times 0.01, or excuse me, 0.1. And if I do my math, that's going to give me, what does this come out to be here? 64, and 16 times 0.1 is All right, I think I had a wrong answer somewhere, so I was double checking here. So we get 64 plus 16 times 0.1, and that turns out to be 65.6. All right, now what you want to think about here is what we've just computed is the change in distance in relationship to the change in time. So what does that mean? It means that the wrench is falling. This 65.6 represents, I think we're in feet here. Okay, so this is 65.6 feet per second. Because remember, the top of this, the change in D represents feet. The bottom of this represents seconds. And since there was no denominator, we just have to assume that that's 1 in the denominator, or 1 second. So in the interval from 2 to 2.01 seconds, that means that this wrench is falling at a rate of 65.6 feet per second. Okay? And now we're going to do another one at 7 and 7.01. So take a look at this. Let's do this interval here. Let me find a different color here. So in this interval, the H value is a lot smaller. It's 0.01. So this time we're going to do the change in D over the change in T. And this is going to equal 32 times 7. So that's my X1. Plus 16 times 0.01. All right. So this one actually turns out to be 224.16. And again, since we're talking about a rate always has two numbers. The top number is dealing in feet, and the bottom number is in seconds. 224.16 feet per second. That is a fast falling wrench, ladies and gentlemen. All right. So basically, I'm just going to write up the second one right here. Let me see. What do we want to? How do we want to say this so we don't have to write too much here? So because these numbers are so close to each other here, look at the interval, 7 to 7.01 seconds. That's awfully close to each other. Even 2 to 2.01 is really close to each other. And you know what I just realized? I just realized that's why my answer was incorrect before, because I didn't do 2.01. I actually did, look at my number over here. I did 0.1. I did 0.1. I missed the 0 in here. So that's why my answer wasn't making sense earlier. So I'm just going to change this to the interval to 2.1. Sorry about that. Hopefully you caught on to that. And so in this second interval, in both of these intervals, the time increase is very small here. So from 7 to 7.01, that's a very short time span. So what we can say here is we can say at approximately 7 seconds, all right, because 7 to 7.01 is very, very short time. The wrench is falling at a rate, okay, of 224.16 feet per second. Okay, and that means that in the first one, at approximately 2 seconds, the wrench would be falling at 65.6 feet per second here. Okay. All right. Now we've got our graph down here. It says the graph shown below is the function and the secant lines found in part C, representing the average rate of change. Interpret the meaning of the lines in context. Okay. So we had our 2 points from above. You know, we've got this blue line down here that represents the first secant line at 2 and 2.01, and the red line that represents 7 and 7.01. And basically what's happening again here is as time increases, okay, so as time increases, all right, we think of those normally as your x values going to the right, but those are actually t values. So as time increases, the rate at which the wrench falls is increasing. Okay? And you can see that in the slopes that we found up above. The first one was approximately 65 feet per second. The second one was approximately 224 feet per second. So as time goes on, that wrench just gains more and more speed on its way down.
That's all, folks.